Greetings to you once again. You are most welcome to Physics with Ben. This is a continuation of the video series Refraction of Light Rays through Rectangular Glass Block, Triangular Glass Prism. In our previous video, we looked at refraction of light through rectangular glass block. We looked at the meaning of refraction, the ray geometry of refraction of light through rectangular glass block. We looked at laws of refraction and where we were able to state Snell's law and all the equations that are involved in the rectangular glass block refraction. We looked at how to verify Snell's law through experiment, the nature of the graph, and what is expected. We looked at critical angle and total internal reflection. However, we rushed over critical angle and total internal reflection. In this video, I want us to just touch a little on critical angle and total internal reflection, and then look at refraction of light through triangular glass prism, and then the equations, and then do some little calculations. Total internal reflection occurs because we did that in the previous video. I'll just repeat it today once again. That's a ray of light traveling from what? From glass to air. We incidence an angle. This is called critical angle. At that particular angle, you have this as your angle of what? Refraction. Normal NO. Critical angle was what I did not explain in that video very well. I mean, total internal reflection was what I did not explain very well. So just click in the description box below and you watch all the videos on this series. So this is what we call the critical angle. The critical angle is given as C equals to 41.8 degrees or 42 degrees. So what we're talking about total internal reflection is that when your eye exceeds this C, meaning a little shifting, taking up of this angle just up here, maybe 43, you know your C is 41.8 degrees. That's your critical angle. And so maybe you have I greater than C, total internal reflection will occur. So in this case, you have your I, which is maybe 44 degrees. Total internal reflection will occur on different surfaces depending on their nature. So maybe for this particular glass, maybe total internal reflection may occur at 45 degrees, 46 degrees, or 47 degrees. But that angle must exceed the critical angle. So when that happens, you have something like this. The glass will now become like the plane mirror surface, and it will behave like the plane mirror, and all the laws of reflection will be applied to it. Now, there are two conditions for total internal reflection to occur. Number one, the ray of light must be traveling from an optically more dense media to an optically less dense media. In this case, the glass media is the optically more dense media, and then the air media is what? The optically what? Dense media. You can sense that even in the refractive index of glass and air. I told us that the refractive index of air, let's say air, is what? 1.3, and that of glass is what? 1.5 to what? 1.7. Condition number two. The angle of incidence from the optically more dense media must be greater than the critical angle. When these two conditions are met, then total internal reflection will occur. This is the working principle of fiber optics. So let us move straight to part B of this lesson. Don't forget to subscribe and share my video to those that need it. Promote this channel and God will bless you. To explain refraction of light through triangular glass block, I will go straight to the geometry of it. Let's suppose we have an equilateral triangle here. By equilateral triangle, we mean this side, this angle, and what this angle are the same. So we have A, and in the school here, and in most school, what we have here, this is the particular one I have in the school. The angle is usually 60 degrees. So in this case, your A is what? 60 what? Degrees. Now, let's label this as our A, B, C. Surface A, B, C. I'm going to produce a video, an experiment on all of this. Now, you have to draw a number perpendicular, maybe at the center here, perpendicular to what? Surface AB. This number, NO, must be what? 90 degrees to this surface. A ray of light will come from this end and will incidence on this surface. Now, this is air. This is what? Glass. This is what? Air. Supposing there was no glass media here, this ray of light would have passed up straight here. Good. But then, so you put your arrow. When you are drawing ray diagrams and the arrow is not there, what you are doing is nonsense. Now, this ray will now bend, will be forced to bend, because we'll be forced to change direction of travel. We'll be forced to bend. We'll be forced to refract. Incident ray, refracted ray, or the bending ray. It will refract and emerge at this point. It will emerge at this point. Now, this emergent ray is stressed backward. These things are drawn one time. It's stressed backward. Now, this is the emergent ray. Now, there is another number here to this surface. Good. Now, this angle is called the angle of what? Emergence. We have NO. Let's call this N prime O prime. So, what you see here, this particular angle is what we call the angle of what? Deviation. This particular angle. And this angle is the same with what? This angle. It's either you pick this or you pick this. Now, this angle is your angle of refraction 1, angle of what? Refraction 2. Now, there is something here called minimum what? Angle of what? Minimum deviation. This one is just angle of deviation. But at the angle of minimum deviation, precisely it is written as what? Small d. Angle of deviation. Angle of emergence. Incident angle. But at the angle of minimum deviation, at minimum deviation, that is dm, it is believed that what? The incident angle is equal to what? The emergent what? Angle. Also, at angle of minimum deviation, it is also believed that what? Our refracted ray is given as what? A all over 2. Meaning 60 of this divided by 2. You may study hard and maybe read your textbook to understand some of this, but these are the facts that you need to know. So for this reason, Mathematically from here, the angle of minimum deviation is given as what? 2I minus what? 2 what? A. Sorry, minus 2I. 2I minus what? 2I. So you can call this equation number 1, call this equation number 2, call this equation number 3. But we say that R is what? A over 2. So equation 3 can make number 4 to form equation what? 4. So we say that this implies that what? dm is equal to what? 2I minus what? 2 times A over 2. This go, this go. So your angle of minimum deviation is what? 2I minus what? A. You can call this equation number 4. Now take notes. Don't ever use the equation we use in the other video to find the refractive index of the rectangular glass block for this. You get it all wrong. However, this guy, the two of them, their refractive index is still 1.5 to 1.7, although they have different equations. They have different equations because their structure is not the same and their geometry is not the same. However, the end result is the same. Good. So, the refractive index of air to glass for a triangular glass prism is given as what? The sine half into what? Angle of minimum deviation plus A divided by what? Sine half of what? A. Sine half into what? Angle of minimum deviation plus A. This A is of 60. Divided by what? Sine half times A. This is the equation to find the refractive index of this glass. Whatever you do, your result must fall in the range of 1.5, that is air to glass or glass to air, must fall in the range of 1.5 to 1.7. I hope that is well understood. Yes, it is. The next thing I want to look at is determination of the angle of minimum deviation via experiments. How can we determine the angle of minimum deviation? Now this is it from what? The equation from the geometry here. This is it from the geometry here. And then this is it from what? The experiments. In the experiment, you'll be asked to plot a graph of what? D. A graph of D against what? I. You'll be given several values of I. I is equal to 30 degrees. 20 degrees, I is equals to 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70 degrees. At each value of I, you are going to have a different value of D. And so, you plot that graph and you will end up having something like this. A graph of D in degrees 0, 0 against what? I in degrees. Such a graph will look like a U-shaped graph where you trace this dot to this place. Where the bottom of this U touches the graph, that place is your angle of minimum deviation. And at this particular point, your I is equal to what? Your E. At this particular point, the value of I here at this point is equal to what? What we have here as angle for emergence. So how do you go about it? You come back here and plug in the value of this in this place, this 60 here, this 60 down, and then you get 1.5, a value within the range of 1.5 to 1.7. This is how to find the angle of deviation through experiments. To this, we have come to the end of this particular section of the video. So, permit me to solve some questions with you. So let's start and go straight to the point. Okay, bring out your calculator and let's do something quickly. I am making use of this textbook, exercise 14, page 306. A ray of light is incident on a body X, as shown in the diagram below. What is the refractive index of the body? This is the diagram. We have what examples. From exercise 14, page 306, question number 1. This is the diagram we have there. You have this as your air media, and this is for the X. Be it glass or plastic, we don't know. So, a ray of light is incidence here, and then we are giving the glancing angle as what? 30 degrees. And then here is, and then bend, then here is 58 degrees. So then once you find the refractive index, it is traveling from air to glass. So write that refractive index of air with respect to glass is given out the sine of I with respect to the sine of R from Snell's law of refraction. Now, some students will just go in and plug in this value that this is your incident angle and this is your refracted. This is your incident angle and this is your refracted angle. That is wrong. Capital wrong. The incident angle or the angle of refraction must take reference to the normal. That is law number 1. The incident ray, the refracted ray, and the normal, they all lie at the same point. So here what do? We say 90 minus 30 will give what? 60. So this angle is what? 60. So this is your I. Here, what do you have? 90 minus 58. You have what? You have 32. So you're going to make use of 60 and 32. So in this case, this implies that your Na to glass is equal to what? Sine of what? Sine 60 divided by what? Sine what? 32. You do that correctly, what do you have? You have sine 60 divided by what? Sine 32. That will give you 1.63. A to glass approximately is what? 1.6. We need a range of 1.5 to 1.7. So this means that this material X is a glass media because the refractive index falls within this range. Lovely. Question number 5 from this same book. Question number 5, page 307. The speed of light in air is 30. VA is what? 3 times 10 to the power 8 meter per second. If the refractive index of the light from air to water is this, refractive index, if the refractive index of the light from air to water, air A to water, is given as what? 4 over what? 3. Then, which of the following is the correct value of the speed of light in water? W, this is not given. Recall that I said that air to glass is going to be sine of I over sine of R equals to V A over V G equals to. Let's stop there. So in this case, that went down to lambda A over lambda what? G. So in this case, we change this G to W, this to what? W, and this to W. However, we are making use of just this and this. So we equate this to this and then we get our answer. So we have A and W is equal to what? V A over V what? W. This to this is given as this. So this implies that 4 over 3 is equal to what? Is equal to what? 3 times 10 to the power 8 meters per second divided by what? VW. This I told you that when they are traveling V is equal to F lambda. This will change, but the frequency will remain constant. So the speed will definitely change. So this implies that 3 times 10 to the power 8 cos multiplied times 3 is equal to what? 4V